last time we talked about extrema, and so extrema are sort of the highest points and the lowest points in a graph. These are features that we're looking for. And so we started by talking about absolute extrema. And so I want to finish up the example we were doing discussing absolute extrema. But by way of review here, I want to start by talking about the definition of a critical point. Regardless of whether we're trying to find absolute extrema or absolute extrema or local extrema, in both cases, it involves critical points. So let me start with this definition here of the critical point. So if the point x equal to c is in the domain of f of x, and if f prime of c equals 0, or if f prime of c is undefined, then the number x equal to c is called a critical point of the function f of x. So a critical point makes the derivative of the function either 0 or undefined. But the critical point also has to be in the domain of the original function. That part is important. So to find absolute extrema, we have the following procedure. So here, given a function, a continuous function f of x, and a closed interval, for example, we use what's called, the book calls this the closed interval method. So basically, what we really want to do is we want to evaluate the function at the critical points, and we want to evaluate the function at the endpoints. So of course, to evaluate the function at the critical points, we first need to find the critical points, right? So first, I'll need to find the critical points, then evaluate the function at the critical points, evaluate the function at the endpoints of the given interval. So I'm trying to find f of a and f of b. And then it's really simple. Literally, the largest value, the largest y value, will be the absolute maximum. And the smallest y value, will be our absolute min. So here, we're literally checking the value of the function at the endpoints and at the critical points. The largest of those is the absolute max value. The smallest of those is the absolute min value. And for intervals of this form, minus infinity to infinity, a to infinity, or negative infinity to b, the procedure is still the same. We're still finding the critical points and evaluating the function at the critical points. We're still evaluating the function at the endpoints, but if the endpoint is infinity or minus infinity, the way we evaluate the function is with a limit. So I would quote unquote evaluate the endpoint by looking at the limit as x goes to infinity, if infinity is part of our interval, or as x goes to negative infinity, if that's part of our interval, and check now, If those limits blow up to infinity or negative infinity, then there will be no absolute extrema, or if those limits equal some fixed number, then I want to compare with the value at the critical point and say which one's the largest and kind of analyze the behavior. And I'll do more problems later with domains of this sort, minus infinity to infinity, a to infinity, negative infinity to b. For now, we just look at problems where we're over a closed interval. So we did this first example here where I asked to find all critical points of the function f of x equal to the positive square root of 4 minus x squared. So here, just to review some basic skills, the first thing I did was I found the domain just so I know when I find the critical point, I can figure out, is it, the domain or not. So for this function here, 4 minus x squared, I need that to be greater than or equal to 0. And so when I solve that equation, I get the domain here has to be x between -2 and 2. And now we take the derivative. So here for the derivative, the most important thing that I hope you notice is number one, this is a derivative, and number two, this is a composition of functions. I have the inside function is 4 minus x squared, and then the outside function is where we're a root function here, raised to the 1/2. So for a composition of functions, the way we do a derivative is with a chain rule. And so here I have the derivative of the root function. So bring the 1/2 down times 4 minus x squared raised to the 1/2 minus 1, which is negative 1/2. And then times the derivative of the inside. And the derivative of 4 minus x squared is negative 2x. So then, it's simplified. We get our expression for the derivative right here. And now I want to know where's this fraction 0? Where's this fraction undefined? So a fraction is 0 when its numerator is 0. So I have x equal to 0 is one of our critical points. And the denominator here is undefined at -2 and at +2. And so I take limits to verify that the function is undefined at these points. I don't think you'd necessarily have to full on take a limit. I think you could even just verbally say, here, 2 and -2 make the denominator 0, but do not make the numerator 0. Therefore, the function is not defined at 2 or -2. You don't have to do a limit. I'm just trying to get the most of my tuition. So I took limits, because I can. But you don't have to. So we conclude that here, all 3 points, -2, 0, and 2 for this example, since they are in the domain, and since they make the derivative either 0 or undefined, these are our critical points. So for this function here, positive square root of 4 minus x squared, we end up with these 3 critical points. So the next problem is related to this, but not the same. So be very careful with this next example. So we are asked to find the absolute extrema, absolute max and min value of the square root of 4 minus x squared, but be careful, here now we have a domain restriction. So it's not exactly the same as the previous example. In the previous example, we did not have a domain restriction. So let me remind you now, I want to check the value of the function at the critical points and at the endpoints. Here, because the domain is -2 to 1, the only critical points are -2 and 0. Those are the only 2 critical points that are in our domain. -2 and 0. So here, 2 clearly is not in the so 2 we do not include for this example here where the domain is -2 to 1 as a critical point. So now I want to check, remember, we're checking the function value at the critical points as well as at the endpoints, -2 and 1. So -2 is both an endpoint and a critical point, so obviously I can just check that once. So here I plug in the endpoint 1, so f of 1, I get square root of 3. I plug in the critical point 0, I get f of 0 is 2. And then finally I plug in the critical point -2, and there when I plug in -2 I just get 0. So now what we're doing is we're looking at the y values. So I'm looking at √3, 2, and 0. The largest of these is our absolute max. So 2 is this, square root of 4 is a bit bigger than square root of 3. So 2 is going to be our max. And here, 0 is this going to be our min. So here are the conclusions. So we have an absolute maximum at x equal to 0, and the absolute maximum value is 2 at x equal to 0. And there's an absolute minimum at x equal to -2, and the absolute minimum value at x equal to -2 is 0, f of -2 equal to 0. So that's the basic procedure. Find the critical points, find the endpoints, plug them in the function. The largest value is your absolute max value. The smallest value is your absolute min value. Things to look out for. just to make sure that the critical points you're using are in fact in the given domain. You know, here I was trying to be sneaky, so I purposely made the domain a little smaller so that not all of the natural critical points of the function could be used. Right? In this case, 2 gets left out because of the way I picked the domain. So absolute extrema is fair game for the test next week. Finding local extrema, or even local extrema in general, will not be on the test next week. That will be on test 3. So the full discussion of local extrema occurs in section 3.3, which is on Friday, and which is beyond the scope of coverage for exam 2. Section 3.3 will be covered on exam 3. So the last slide I want to talk about here to finish up section 3.1 is to discuss this notion of the derivative as a gradient vector. So I just want to warn you, this material is not in our textbook. I've never seen it in any textbook. I don't even know if there's any calculus Calc 1 class that's going to talk about this material. But this is really important. And this has to do with the way we study derivatives in Calc 3. And this hopefully will, help understand what happens in Calc 3 and alleviate any confusion, okay? So very quickly, in Calc 1, we kind of do things in a very classical way. And in Calc 3, we start to use more modern math, such as vectors, okay? So a vector can be thought of as a mathematical object that has sort of 2 components, a magnitude and a direction. And most of you have seen vectors in physics, and in physics, the vectors are arrows. Vectors are much more complicated than just arrows, but for now, let's just pretend like vectors are just arrows with, a length and a direction. So what we're going to do is to first think of the graph of y equal to f of x as being drawn by the tip of the vector x comma f of x. So what does that vector look like? Well, starting at the origin, it's just an arrow that points to that point. And so now what we're doing is we're plotting each of the points for x from smallest to largest in the domain. And the vector, the tip of the vector, as we plot the points, the tip of the vector will draw the curve. So here, as we run x through the domain of the function, the vector draws out the curve, the tip of the vector. The vector acts like a pen, okay? So here, this is what's known as a parametric curve. And you'll study this in Calc 2. We don't look at curves this way in Calc 1. As I said, this is a very modern way of looking at math. But now, once we have this function drawn, with the vector, instead of talking about the derivative directly, we talk about what's called a direction vector of the tangent line. So here we have a vector of the form 1 f prime of x. The 1 means that the vector will always point to the right. The f prime of x, if f prime of x is positive, the vector will point up. So here, where the function is increasing, you can see the direction vector of the tangent line is pointing up. And of course, the f prime of x is the slope. And whenever f prime of x is negative, then my direction vector of my tangent line will point down. It'll point to the right because the x coordinate's always 1, and then it'll point up or down depending on if f prime is positive or negative. And again, you see the direction vectors right here for this, I did sort of 2 examples here, right? Direction vectors. And using the direction vector, we can solve our Calc 1 problem of finding the slope of the tangent line, right? That second component of our direction vector here, f prime of x, gives us all the slope information. So this is a very Calc 3 way of looking at this stuff. And now this is the point, this is the part I wanted to talk about. So the derivative actually has another life. We think of the derivative as telling us about the slope of the tangent line, right? We use the derivative to tell us if the function is increasing or decreasing, if the slope is positive or negative, But we can also interpret the derivative as being a vector or an arrow that lives in the x-axis only. Okay, so this is the gradient vector part that we don't talk about in Calc 1. So if we think of the derivative as a vector completely living in the x-axis, so it's an arrow completely living in the x-axis. And so how does the vector work? So if the function is increasing, then in the domain at that point, we put an arrow pointing to the right. And the length of the arrow will be equal to the absolute value of the derivative at that point. And so you can see here, the function is increasing. And so in the domain, I've got an arrow pointing to the right in both pictures. And if the function is decreasing, if f prime of x is less than 0, then in the domain, we're going to put down an arrow pointing to the left. So here you see the function is decreasing. And for the gradient vector part in the domain, I put an arrow pointing to the left when the derivative is negative. Okay? So this vector in the x-axis, when we interpret the derivative this way as an arrow in the x-axis, it's known as a gradient vector. And the property of the gradient vector that we notice is that the gradient vector always points in the direction that will make f of x increase. Like here, if I move to the right, if I take the x values and move them to the right, and then you look at the curve, what happens to the curve when you move the x values to the right? The curve increases. Again, for this other vector here where the curve is decreasing, if I move to the left, if you look at the y values, what happens to the y values if we take the, decrease the x values here for this first picture? Oh, the y increases. And even with the other graph here, if I move to the left, the function will increase. If I move to the right, the y value up here will increase. So this interpretation of the derivative as a vector in the x-axis is a really important one. And we don't do it in Calc 1, but it comes up later in Calc 3. And it has this wonderful property that it always points to the direction where the function increases immediately. What do I mean by immediately? I mean the fastest. Here, that doesn't make sense when you're dealing with two-dimensional curves. But think about climbing a mountain. What's the fastest way to get to the top? It's the steepest way is the fastest way to get to the top. And that's the direction the gradient vector usually points in. The steepest way, the fastest way to get to the top. So, if you don't like this slide, then I want you to forget about it and never look at this slide again, okay? So like I said, I doubt this is taught in any other Calc 1 class. I just wanted to bring it up because I know this comes up later in Calc 3 and it causes some confusion. And I just want you to remember that the derivative actually has two lives. It's not just, this tangent line stuff. That's true, but there's also this gradient vector component to the derivative. Okay, so having said that, you'll never be tested on this in this class. You'll never see this again. I'll probably never mention it. And let's just all pretend like I never talked about it. So that ends section 3.1. And so now, without any further ado, let me start section 3.2. And section 3.2 covers what's called the mean value theorem. So this is an extremely important, if not slightly random theorem. The fact of the matter is, mean value theorem is really important, but it's always in the background. So we never really see how important it is. In this class, in Calc 1, mean value theorem will be what makes integration work. And that's why we really are studying mean value theorem, so that we can use it in chapter 4. So it's a bit premature and random to introduce it in section 3.2, but here we are. So before I talk about the mean value theorem, I have to talk about what's called Rolle's theorem. So there's Rolle's theorem, and then using Rolle's theorem, we can prove the mean value theorem. And I think it's really important to frame Rolle's theorem properly so that we know why we're even looking at this theorem. You know, I could just give you the theorem and say, here, memorize the theorem, but I'd rather kind of motivate it. I'd rather say, okay, what's the theorem about and what's the result we're getting? So here's the game we're playing. Suppose we only have 3 pieces of information about the function f of x. Okay, we only know 3 things. We know 1, that the function is continuous on this closed interval, continuous on the closed interval. 2, we know the function is differentiable on the open interval. And 3, the last piece of information that we know is f of a equals f of b. So what does that mean? The function starts and ends at the same height, okay? So if we know these 3 facts, that the function is continuous on the closed interval, differentiable on the open, and starts and ends at the same height, what mathematical facts can we discover about f of x, f prime of x, and the domain? So this is now our motivating question. If we only know these 3 pieces of information about the function, that it's continuous on the closed, differentiable on the open, and starts and ends at the same height, what mathematical facts can we uncover? So I just want to now analyze the behavior of the function. By the way, the slides you have might say motion in 2 dimensions at the top, and I changed it to curves in 2 dimensions. I wanted this to be a discussion about the geometry, and to me the word motion tends to be more of a discussion of the physics. So here, just you know, think about the very basic scenario that we have. That I've got, so let me put up an axis here. There's my y-axis, here's an x-axis. I've basically got a function that's starting and ending at the same point. So maybe this is the starting point, this is the ending point. And the height is the same. So the question is, in how many ways can this happen, right? The most obvious way is just take a direct path. Just go directly from one path to the other. Just go straight. So if we're going to start and end at the same height, one way this could happen is if we take this direct path, you know, the path of the easiest path, from just point A to point B. In this scenario, if we take the direct path, we can conclude that the derivative along the line is 0 because it's a horizontal line. Remember, I'm trying to find things we can conclude. So if we take a direct path, here's one thing I can conclude for sure. I'm not saying it's super deep, but this is a mathematical, you know, conclusion that we can arrive at. So now, what if it's not a direct path, right? So instead, so now suppose this is my starting point. This is my ending point. Suppose the curve starts by going up first. So if the curve goes up, now think about flying a plane, okay? So the curve goes up first, but eventually I need to get back down to the original height. So right here, you'll notice the slope, because it's curved up, you know, compare it with the slope of the direct path, which is this dashed line. The slope here is greater than 0 since we went up. Now think about you're flying a plane. So I pull up, going up, but now I have to get back down to the same height. So here, to come back down, here you'll notice the derivative is negative because the function's decreasing. So between the derivative being greater than 0 and the derivative being less than 0, at some point or more than one point in the middle, it looks like the derivative will be equal to 0. I mean, if I go up, I have to come back down. And if I go up and I'm coming back down, at some point I need to level off. When I level off, the derivative is 0. So again, we've come to the same conclusion as case 1. So for what goes up must come down, starting from the left endpoint, if we go up, then eventually we'll have to come back down, you know, so that we can end up at the same height. And so if the derivative is greater than 0 and then comes back down to less than 0 at some point in between, call that number C, the derivative must have been equal to 0. So at least 1 point. We've come to the same conclusion as when you take the direct path. The other option is, instead of, what goes down must come up. So instead of starting by going up first, so now here's my starting point. Here's my ending point. And now suppose we go down first. So well, here the derivative is going to be negative. So here I'll have f prime is less than 0. And think about you're flying a plane. If I want to end up at the same height, then if I went down first, then at some point I'm going to have to pull up. And so here f prime is greater than 0. So in between the derivative being less than 0 and the derivative being greater than 0, we believe there's a point in between where, or at least one or more points where the derivative must have been 0. Again, if you're in a plane and we go down first and we want to head back up to get that original height, then I have to level off and then pull up. When I level off, the slope is 0. So again, in scenario 3, starting from the left endpoint, if it first goes down, then at some point it has to come up. And so in between, when it goes down and comes up, the derivative will be exactly equal to 0. So now, of course, the natural question is, well, what if it goes up and then comes down and goes up and comes down? If it has a path like this is just a combination of cases 2 and 3, right? Case 2 and 3 are your fundamental ways it could move. Case 1, it could just go the direct path, or it go up first and then come down, or it could go down first, and then anything else is just a variation of cases 2 and 3. So anyway, this little thought experiment, which is totally not rigorous, but we're analyzing the behavior, the path of a curve in 2 dimensions. In this scenario, we conclude that there's probably a number in between A and B such that the derivative is 0, i.e. the plane has to level off at some point. If it's going directly, then it's always level. If it goes up and then comes down, it has to level off. If it goes down and comes up, it has to level off. So this is called Rolle's theorem. So Rolle's theorem, theorems are typically if-then statements or if and only if statements. So this is an if-then statement. So here's the hypothesis. We need 3 conditions have to be satisfied. We have a function that's continuous on the closed interval a to b. We have a function f of x that's differentiable on the open interval a to b. And we have a function such that f of a equals f of b. The height at the left endpoint is equal to the height at the right endpoint. So then according to Rolle's theorem, in this scenario, then there'll be at least one number inside the interval ab such that the derivative at that number will be 0. So there's at least one horizontal tangent here. And here, I've done the 3 different scenarios we think about, and in each case, at some point, the point has to level off. If I'm gonna stay at the same height, at some point, it's gonna have to be parallel. Whatever path I take at some point will have to be parallel to this most direct path. If we're not actually taking the most direct path, any other path at some point will have to be parallel. So that's Rolle's theorem. And Rolle's theorem seems kind of pointless, it's like, oh great, what's the big deal? But it is a very humble starting point for proving very, very powerful mathematical results. So the direct theorem that comes from Rolle's theorem is the mean value theorem. And the mean value theorem is a really powerful theorem. So in Calc 1, it makes integration work. In Calc 2, it makes Taylor's theorem work. In Calc 3, it'll make this whole bunch of these surface integral theorems like Green's theorem work. Okay, so that's why we study mean value theorem, but it's always in the background. You never explicitly notice when you're studying Taylor's theorem, no one will ever say the word mean value theorem. When we're looking at, Green's surface integrals in Calc 3, no one ever says the word mean value theorem. But at the end of the day, if you follow the math, mean value theorem is really important. So mean value theorem is an if-then statement. It has two hypotheses. We require a function f of x that's continuous on the closed interval a to b, and a function f of x which is differentiable on the open interval a to b. And so here's the conclusion. Then there exists at least one number in the interval, call it c, such that f prime of c equals f of b minus f of a over b minus a. So I'll discuss what this means in 1 second. I just want to mention the other form of mean value theorem. I also like to think about it this way, is to take the b minus a and move it to the other side. So this is actually the way we will use mean value theorem shortly here, in chapter 4 when we try to do integration. So this is, I like to think of both of these versions. Either f prime of c equals f of b minus f of a over b minus a, or f prime of c times b minus a equals f of b minus f of a. You're just moving the b minus a term over. So here's the picture of the mean value theorem, right here, this one here on the right. This number here, f of b minus f of a over b minus a, that's the slope of the most direct path. So if you take the most direct path from a f of a to b f of b, which is that line, the slope is f of b minus f of a over b minus a. So the theorem is saying that at some point when we travel from a f of a to b f of b, at some point the tangent line will be the same as the slope of this direct line, will be parallel to this direct line. And it kind of makes sense, the proof sort of works the same way Rolle's theorem did, okay? So here, let's call this slope here of this most direct path, let's just call that slope m, just so I don't have to write down. So here, f of b minus f of a over b minus a is a number that I'm calling m, okay? So try that again, m. So look here. In the picture, we're not taking the direct path. Of course, if we take the direct path, then there's certainly a point where f prime of c equals m. In the picture here, I've started by going above the direct path. So what does that mean? Right here, the slope is greater than m. It's more steep than the direct path. But if I eventually want to get back down, after going up above the direct path, I'm going to have to come back down. Here, the slope is actually negative because it's decreasing. So here, the slope is actually less than m. In this picture, you can see the slope is a positive number here. And so in between, it starts out the slope is bigger than m. It ends up the slope is less than m. In between, there must have been at least one point where the slope is identically equal to m. It's the same idea of Rolle's theorem. And the idea is that to get from a comma f of a to b comma f of b, to get from the left point to the right endpoint, the quickest way is using the most direct path, which has this slope f of b minus f of a. Any other path that's not the most direct path at some point will have to be parallel to the direct path. The way I think of any non-direct path, like this path here, that's the non-direct one. I kind of think of it as we took the direct path and we broke it up into little steps here and just kind of spread it out. It's not the most efficient because we're taking the direct path and we're arcing it up over in this case. But there's no way to avoid the direct path. And, when you go from the left endpoint to the right endpoint, any path you take, if it's the direct path or not, at some point will have to be parallel to the direct path. There's no avoiding, going in this direction at some point. So I'm going to let you think about that. Oh, in terms of the proof, typically starting out with Rolle's theorem, this isn't a mathematical proof. This is just to kind of give you the idea. The idea is that we take one of these endpoints and pull it up, that tilts the whole picture. If I pull up this endpoint, it kind of tilts the whole picture. And so that's where we get the mean value theorem from. Of course, the proof is much more rigorous than that, and it's in the book. And this is not a proofs class, so I'm not going to go into it. But that's how they're that's one way to think about how they're related. that the mean value theorem is sort of a tilted version of Rolle's theorem. You know, where here we have a horizontal line, but in the mean value theorem, you know, we have this angled line, and we've just tilted the picture. Okay, so I just want to make some comments about why we care about mean value theorem and then do an example. So as I said, the real use of mean value theorem will be in chapter 4. Okay, first let's demystify the term mean value theorem. What the heck does that mean? So the word mean is a word from statistics that refers to the average. In this case specifically, the numerator is calculating the height change and the denominator is calculating the width. So here we're calculating the average change in height over the given interval. You know, suppose the given interval is 2 units long, and suppose the height went from 0 to 10. Then the average change per unit would be an increase of 5 units in height. Because at 0, it's at 0, at 2, it's at 10. On average, it increased about 5 units per, you know, every step in the x direction. So that's why it's called the mean value theorem, because it has something to do with averages, okay? Here's a nice result from the mean value theorem. And it's not a very deep one, but it is profound. We can prove that if f prime of x is equal to 0 for each x in an interval, then f of x is a constant. So, you know, it's not complicated, but it is profound because this is our first example of an antiderivative. You should look and see what this statement just did. It started with a derivative. It said if f prime of x is equal to 0, and then it concluded something about f of x. We haven't done that in this class before. Up until this point, we've always started out with f and then found the derivative. So this is our first example of an antiderivative, and this is one of the reasons mean value theorem is so important. It starts to introduce the concept of antiderivative. By the way, this is also a very trivial differential equation, but this is also, you know, our first differential equation that we've solved. You know, antiderivatives and differential equations are a big part of calculus. So here's another integral or antiderivative type result that we can prove using the mean value theorem, and I don't go over the proof. If f prime equals g prime for all real numbers, then f of x equals g of x plus c. What you should see here is that we reversed the process. We had an equation involving derivatives, and we went backwards, and we found the antiderivative, or we undifferentiated it. You know, this is what an integral will do. An integral will undifferentiate something. That's not a word. Don't ever use that word. So as I said, you know, to be perfectly honest with you, and that's what I'm always going to be, the introduction of the mean value theorem at this point of calculus is random, is kind of random. It's kind of like, wait, what? Why do we need this? And like I said, the real reason we need mean value theorem will be in chapter 4 for integrals, okay? And so you'll see in the rest of this section, we'll be doing mean value theorem problems that are just totally random, okay? Because the real reason we're going to use mean value theorem is in chapter 4. So let me give you just a quick taste of how we do that. In the mean value theorem, let's choose the number b in the interval a to b. Let's choose b to be a plus delta x. And for the heck of it, just to make things simple, assume delta x is positive. So I'm looking at a, and I've just moved a little bit away from a. So if the function is continuous and differential and all that stuff, the mean value theorem says there's a number c in the interval such that, so there's a number c in the interval such that f prime of c equals f of a plus delta x minus f of a over a plus delta x minus a. In the denominator, you can see the a's cancel. Now take this delta x and move it to the other side. So then that gives us this equation, f prime of c times delta x equals f of a plus delta x minus f of a. So this equation, while it looks very simple, this will be the equation that allows us to do integration. And I know, I told you to always read an equation left to right and right to left. Here, the really important direction we want to look at this equation is from left to right. What you should notice is that we were able to replace this expression, which involves a derivative. We're able to replace it with this expression on the right-hand side, which has no derivatives in it, involves the antiderivatives. Okay, so this equation here in the red box on the right will be used to build a definite integral in chapter 4. And the derivative here we see acts as a conversion factor. So what you should notice is delta x is length in the domain. So delta x was actually a plus delta x minus a. You know, when we found delta x, we were actually calculating a length on the x-axis. You know, I was doing a plus delta x minus a. And so here's length in the domain, and f of a plus delta x minus f of a, this is a height. This is measuring distance in the range. And so here we have f of a plus delta x minus f of a. That's a length measurement. That's a height in the range. And so here, the derivative is acting like a conversion factor. It allows us to relate. So this derivative right here, just hanging around, is acting like a conversion factor. It's allowing us to relate length in the range with length in the domain. And, you know, we can eventually use this equation to create integrals and to evaluate, basically to eliminate the derivative by replacing it with its antiderivative. So here in particular, look at this equation from left to right and notice that on the left side, I have this expression that involves a derivative. However, on the right side, the derivative has disappeared. So we've undifferentiated it. We've done an antiderivative. We've done an integral. You know, we'll introduce those words later. So this is the real reason mean value theorem is important, but we won't talk about it until chapter 4. So now in section 3.2, you'll just see a bunch of random problems. The only thing they have in common is that they use mean value theorem. Okay, so if you're doing homework in section 3.2 and you're like, what? I don't get how this fits with anything. That is totally, that's how you should feel. Yeah, that's totally right. As I said, mean value theorem will really play a big part in chapter 4, but it'll just be in the background. You know, I'll point it out, but in the theory, it's just kind of hanging around in the background. So here's a very artificial problem. I just want to find all the numbers C that satisfy the conclusion of the mean value theorem for the function f of x equal to cube root of x on 0, 1. What does that mean? Remember, the mean value theorem says there's a number C such that f prime of C equals f of b minus f of a over b minus a. So I want to find that number C. In this case, the function we're being given is the cube root function, and the interval a to b that we're asked to look over is 0 to 1. So I want to find a number C such that f prime of C equals f of 1 minus f of 0 over 1 minus 0. Okay, that's all this is asking for. So just to be very mathematical and precise, I first establish the hypothesis of mean value theorem. I first point out that the cube root function is continuous on the closed interval. So think about the domain of the cube root function. The cube root function is a very well-defined function. It's defined for all x, so it's certainly continuous on 0 to 1. And then I take the derivative. And so here's the derivative. And I say, well, look at the derivative. It's got a denominator, and the denominator can't be 0, but this derivative is defined on the open interval 0, 1. No problem, since 0 isn't included. So I've established the two hypotheses for the mean value theorem, that it's continuous on the closed, and differentiable on the open interval. So now we can evoke the mean value theorem and claim by the mean value theorem there's a number C in the interval 0 to 1 such that f prime of C equals f of 1 minus f of 0 over 1 minus 0. Now we're just doing algebra. That's really all the theory part. Now we're just plugging and chugging. I now need to calculate f prime of C will just be f prime of x, where the x is replaced by c. F of 1, I'm looking at this function here, f of x, and using that to calculate. F of 1 will be the cube root of 1, which is 1. F of 0 will be the cube root of 0, which is 0. So here in the numerator, I'll have 1 minus 0, or just 1, divided by 1 minus 0. So I get 1 over 1 on the right-hand side of the equation. And so I get 1 over 3 times c to the 2/3, which is just the derivative evaluated as c, is equal to 1. 1 was just, you know, what this f of 1 minus f of 0, this stuff just evaluates to 1. Now I'm doing algebra. So I basically just cross multiply. I take this c to the 2/3 that's in the denominator down here, and I move it up here. So then I get c to the 2/3 equals 1/3. Now cube both sides to get rid of the cube root on the left. When you cube both sides, you get c squared equal to 1 over 27. Okay, now be really careful. The algebra here, technically speaking, if c squared equals 1 over 27, then c equals the square root of 1 over 27. That is, c equals plus minus root 1 over 27. But of course, we don't use both roots. In this case, we have a domain restriction. So we're only going to use the root that's between 0 and 1. Obviously, it's the positive root. You know, since I'm a mathematician and I'm kind of a math nerd, I proved that square root of 1 over 27 is positive and in the intervals 0 to 1. You, of course, don't have to do this. I did it because, as I said, you know, I'm a mathematician and I just want to get the most out of my tuition money. So for you, you can skip all this part where I prove the square root of 1 over 27 is in the interval 0 to 1. You can just do that right there. You can say, okay, c squared equals 1 over 27. So c is plus or minus square root of 1 over 27. And now I need to pick the root that's between 0 and 1. And so that's obviously, quote unquote, obviously, you know, the positive square root of 1 over 27. And so this is my final conclusion here that, oh, the number c in 0, 1 that satisfies the mean value theorem for the cube root function is, you know, 1 over the square root of 27. So yeah, here this part is, you know, bonus math. I mean, I just, like I said, I wanted to get the most of my tuition money that I paid to learn all this math. So that you don't have to do. I just basically proved that the denominator is bigger than the numerator and that both terms are positive. So that proves it's greater than 0 and less than 1. And as I said, you can just ignore all that. So I have 2 more examples, but it's 3:48, so I'm not gonna, you know, start too early. So I will finish up the last 2 examples next time. This is the cutoff for the test, section 3.2. Okay, mean value theorem and Rolle's theorem. And, you know, something artificial like this is definitely conceivable because, as I said here, we're really just doing mean value theorem for something else in chapter 4. All right, folks, I'm going to stop right here.